there's all sorts of different types of chemistry problems. There's the problem part, and we're going to talk more about chemistry problems today. But honestly, to me, there's almost when you're working problems, you have to keep in mind what those problems mean as you're working them in order to benefit, because it can come back to, it will make the problems go easier if you understand what you're doing. And then later on, as we kind of come back around, it will help too. So we talked about molar masses in Unit 1. You're like, Mrs. Snipes, this is Unit 2. Why are you talking about molar masses? And actually, we're going to take it up a notch. When we talked about molar masses, we talked about the molar masses for the elements. Use that decimal number. So we know that the molar mass is just the grams to get 1 mole of those things, and we applied it to elements. Units of molar mass are grams per mole, grams/mole, G over moles, or if you want to go ahead and use the mole raised to the negative first power, you can. It's all about units in working physical science problems, including chemistry problems. So we applied it for the elements. These are some compounds. So kind of starting up here, we have 1 octanol, and here this is mercury 2 iodide, the pretty orange powder. This is methanol, and this is sulfur. Now sulfur, or not just any sulfur, this is sulfur with a repeating unit of 8 sulfur atoms. Okay. Now in each one of these containers is 1 mole of those molecules. Okay. So there must be a molar mass to get to molecular molecules to compounds. So molar mass, we said for atoms, it's that decimal number, which is the average atomic weight for the molar mass for the elements. For compounds, it's not so surprising, and you can convince yourself of this to be true. But when we met in here on Monday, we came up with molecular weight. How much does a molecule of water weigh? How much does a formula unit of NaCl weigh? We call that molecular weight and formula weight. Well, for those compounds, the molar mass is equal to those weights, but of course those weights are in AMUs, but kind of like we did for elements, we have to switch to grams per mole. Okay, so they're numerically equivalent, but they have different units. Molar mass, the units are always going to be grams per mole. How do you get to the molar mass for compounds? You basically do what you did with your homework today. You knock out the molecular weight or the formula weight, and it's that number, but it's units of grams per mole. So when we're talking about the weight, not molar mass, but the weight of an individual atom and the weight of an individual molecule or formula unit, those are always going to be in units of AMUs. Molar mass is in grams per mole. Grams per mole, molar mass. So if you want to know how you can use something like a property or constant like molar mass as conversion factor, you look at the units. So it's our link to go back and forth between grams and moles. So let's do a few. Let's just simply come up with the molar mass of ethane, which is a molecular compound, and ammonium chloride, which is an ionic compound. This is going to be deja vu. We want molar mass now, not a molecular weight and formula weight. So the units are going to be grams per mole. Now this says in italics explicitly labeled. When I come up with a molar mass, for example, ethane, I'm not going to do it this way, but I'm just showing you how it works. From the formula of ethane, C2H6, we know we have in 1 mole of the C2H6, we would have 1 mole of carbon atoms. So 1 mole of carbon atoms and 1 mole of compound. Decimal number for carbon is 12.01 grams per 1 mole of carbon. Then we need to account for the hydrogens. According to the formula, we have 6 moles of hydrogen atoms for every 1 mole of the compound. So decimal number for hydrogen is 1.008. That's the molar mass for hydrogen, grams of hydrogen per 1 mole of hydrogen. We go ahead and knock that out on our calculator, and it's 30.07. Units for molar mass for a compound like this, or molar mass for anything, is grams per mole. And if I was working this on, if this was the only thing of interest in my problem, I probably wouldn't even be as explicit as to say C2H6. I would just say it's 30.07 grams per mole, just so as you know. Working the same problem the way I would do it, it looks like this. And I kind of mentioned this the other day. I know from the formula I need 2 carbons. The decimal number for carbon is 12.01. 6 hydrogens. The decimal number for hydrogen 1.008. And of course we get the same number. Okay. Now, this idea of coming up with a molar mass for a compound is often the first step in working maybe more complicated problems in chemistry. You always have to show the molar mass calculation. In fact, in my answer keys, and probably even if I wasn't preparing an answer key, a lot of times I will label my step. I'm like, molar mass, it'll say MM for molar mass, and I'll put the compound formula, and then I'll go ahead and knock it out. Always show your work. Problem is, if on the test tomorrow, even if you get the right answer, but if you don't show me all your calculations, sorry, you won't get full credit. But kind of along those lines, if you show me your thought and you don't get the right answer, then you definitely get a lot of credit if it's correct. So ammonium chloride, let's knock it out, and let's do the abbreviated way instead of the difficult way. So you need to count for nitrogen. Decimal number for nitrogen is 14.01. 1 times 14.01. Account for hydrogens, 4 times 1.008. Account for that 1 chlorine, so that's 1 times 35.45. I think one of my next slides coming up maybe will be something that I've alluded to before, and something that's heavier than 10 with regard to whether it's molecular weight, formula weight, atomic weight, or whether it's molar masses. You're going to go with 2 decimals. So 2 decimals, you're looking at 53.49 grams per mole. Okay, for the compound. And then I don't have a problem, or yeah, it's supposed to be coming up. But remember, anytime you see something slash something, remember the units, the first units are in the numerator and the second units in the denominator. So I could unpack this, and that would mean 53.49 G grams over 1 mole, where that 1 in 1 mole brings no uncertainty. Molar mass of ammonium chloride. All right, well, so for things, whether it's molar masses or weights that are less than 10, generally shoot to be giving it 3 decimals. And I think I said the other day that kind of narrows things down. With boron, you're getting a weight of 10 point something. So less than boron, beryllium, lithium, helium, and hydrogen, you're going to use 3 decimals basically. If you do that, what that will do is in your answer, you're going to be justified 2 decimals. And with 2 decimals and a number 10 or larger, that gives you 4 sig figs. All right, so let's work a problem. So remember, the thing in brackets might not be there for the problem to be correct. So how many moles is 1.28 grams of chloroform? So if I was going to kind of diagram this, I'm going to go from grams to moles, and usually I just put MM for molar mass. Use molar mass of CHCl3. So I kind of said molar mass is a side calculation before you work the real problem, and so that's exactly what I'm going to do. So here we go. Let's use the abbreviated approach to knock out the molar mass for CHCl3. So we have 1 times 12.01 plus 1 times 1.008 plus 3 times 35.45. So you're looking at a molar mass of, with 2 decimals, because that's what you're justified, 119.37 grams per mole. So remember what this means for this compound. That means 1 mole of CHCl3 per 119.37 grams of the compound. That's what molar mass means. We did problems like this before. That's actually going to be my second term. My first term is going to be the thing I want to convert. So if I'm starting with grams, am I going to use the molar mass like this or flip it? Flip it good. So my first term is 1.28 grams. Notice I don't write CHCl3. There are types of problems where we have to be explicit, but since I'm only one compound, I don't need to. You said I'm going to flip the molar mass, and I am. So my first term would be 1.28 grams. I would probably put over 1. And then my grams will cancel, and I'm left with units of moles, which is great. So get your finger ready. How many sig figs? Like in 3. Very good. So to give 3 sig figs, this 0 is not significant, but the 0 between the 1 and the 7 is. That's another thing on your test. I'm going to be pickier grading your test than I am your homework or even your labs. So problems like this would be worth multiple points. So to get all the points, you have to round correctly too. We good with that? Okay. Let's work another one. And in this case, we're going from moles to grams. And we're going to do that using the mm, or molar mass, of CH4. All right, here we go. So, using the periodic table, we're going to take 1 times 12.01 for carbon, plus 4 times 1.008 for hydrogen. We're allowed 2 decimals in our answer. That gives us a 16.04 grams per mole. So for CH4, that means there's 16.04 grams of CH4 in 1 mole of CH4. So my first term is going to be moles of CH4. So do we leave this as it is or flip it?
Yeah.
Leave it, yep. So my first term is going to be the 0.4444 moles over 1. We just bring down the molar mass, 16.04 grams over 1 mole. The moles cancel. We have units of grams, and how many sig figs? 4. Yep. So with 4 sig figs, you're looking at a mass of compound is 7.129 grams. I think I mentioned this before and become more obvious when we do more problems, but in dealing with the chemistry of the way stuff reacts and interacts, it's about moles, not about grams. So it's important for us to be able to go back and forth between grams and moles. So molar mass is this sort of basic problem is an important one. All right. Well, let's switch it up a little bit. Again, that thing in brackets may not necessarily be there. So it'd be how many moles of Br or Br atoms of Br are there in 1.92 grams of the compound that has a formula of CBr4. So we want individual bromine atoms from the compound like this. Well, we know that we can go from grams of CBr4 to moles of CBr4 using the molar mass, right? But to get all the way from moles of CBr4 to moles of cute little bromine atoms, we're just going to have to recognize, and I'll put it over that arrow, that for one CBr4 repeating unit, how many bromine atoms do we have? 4. Yep, we have 4. So it's going to be an extra step here. For every repeating unit of CBr4, since the formula is got 4 bromines in it, we're going to have 4 Brs. So we have a 2-stepper. So we can talk about for every 1 molecule of CBr4, we have 1 carbon atom and 4 bromine atoms. We could also scale it up from 1 to a mole. And actually, this is how we're going to use it. If you have 1 mole of the compound, then you have 1 mole of carbon atoms, and you have 4 moles of bromine atoms. Okay. So we're actually going to use this relationship. So there's 4 moles of bromine atoms in 1 mole of CBr4, and that's exactly how you're going to see that ratio inserted in the problem coming up. So here we go. Make sure you show your molar mass calculations. So we take 1 times 12.01 plus 4 times 79.90 for bromine. Heavy stuff. We're allowed or justified 2 decimals, so you're looking at a molar mass of a whopping 331.61 grams per mole. So remember, that means 331.61 grams of the compound CBr4 per 1 mole of the compound. All right, so let's do it. The first term is going to be the mass of the compound, and you're going to see that I am going to go ahead and be explicit. So the mass of the compound over 1. What's the next term?
It's going to be the molar mass of the whole compound.
Yep, it's going to be this molar mass of the whole compound. You think we're going to flip it or use it like this?
Flip it.
Yep, flip it. So if we make our next term 1 mole of CBr4, the compound, over 331.61 grams of CBr4. Well, on the previous slide, from the previous slide, what can we do now as a third term to make moles of CBr4 cancel and be left with moles of bromine atoms?
Do 1, or would it be 4 moles of Br over 1 mole?
Yep. 4 moles of Br over 1 mole of CBr4. Yep. Now grams of CBr4 have canceled. Moles of CBr4 have canceled, and we're left with units of moles of Br. That's it. So how many sig figs? 3. I'm liking it too. So this first 0 here, it's a placeholder to get 3 sig figs. That's what we would report. And that's it. Just in case you guys run up against this, see this phrase right here, 4 moles of bromine. Sometimes it will go like 4 moles Br atoms. And I have been working problems before. I'm like, what in the heck are bratoms? But anyway. Okay. So this is, I've been talking about units. It's all about units. Set up your problem. Make sure that you use the units correctly and get the units that you need. And be explicit means detailed. Be detailed where you need to. So these will be due on Friday. You'd be like, oh, that's harsh. You need to have a test on Thursday and homework due Friday. Yes. So, okay. So let's take a look at hydrated salts. It just sounds so fancy, but they're not really that fancy. I think this would work, it's fair to say. You know, when you buy some things sometimes, like a purse or something, well, guys wouldn't know, but sometimes food, sometimes like beef jerky will have, it says do not eat, it's a desiccant in there, okay? Probably that desiccant may or may not be what's called a hydrated salt. The term salt, if I were to bring up my list of 2 types of compounds, we have molecular compound, ionic compound. I'm not going to draw it up there again for you. But under ionic compounds, I would put the word commonly called salts. So this word salt, it just means an ionic compound. Some salts are very hygrophilic, okay, versus phobic. So they love water, so they'll pick up water. They're stable with a certain number of waters. And if it's oftentimes there's a certain sweet number they have. Those are called waters of hydration. Okay, and so it's a hydrated salt. The opposite of a salt that's hydrated is to, and it can be done with some heat, is to kick off those waters of hydration, and then you get what's called the anhydrous version. Okay, anhydrous, without salt, hydrated salt. It's got cute little waters of hydration around it. It's adorable. And I don't think I finished that thought, but it's a certain number of waters of hydration. It's not random. So, for instance, barium chloride is great. What barium chloride wants to do is for every one formula unit, because remember we call repeating unit of an ionic compound a formula unit. For every formula unit of barium chloride, it wants to have 2 waters of hydration. It just wants to. Not 1, not 3, but 2. The way we would call this formula is BaCl2 dot 2H2O. So if somebody's giving you a formula and they can say the word dot in it, they're like, oh, well, I bet they're going to give me some waters of hydration for that ionic compound. So for every 1 mole of the anhydrous compound, BaCl2, you're going to have 2 moles of waters of hydration. Copper 2 sulfate. Okay, it has 5 waters of hydration. So we're going to work these different types of problems associated with hydrated salts, and we're going to use this to our advantage from the formula for a hydrated salt. In this case, we know that for every 1 mole of the anhydrous, we've got 5 moles of waters of hydration. Iron 3 nitrate, it's got 9 waters of hydration. So this is where sometimes in chemistry, if I'm doodling a problem, depending upon how difficult the problem is, I will literally write, I'll do a picture of FeNO33, okay, and then I'll write 9 little waters nested around it, just to kind of picture what that looks like. Now, in not this unit of material in general chemistry, but maybe it's unit 3, I think it's this unit. Anyway, in one of the units, we're going to actually talk about what's called nomenclature, how you name things. And I'll tell you that this whole di for 2, penta for 5, and nano for 9, I'll try to explain it when we get to naming things, but we're going to steer clear of those. Okay, but anyway, but we do call it barium chloride dihydrate for the hydrated salts. Pentahydrate, non-hydrate.
I have a question.
Yes.
Sorry if I'm not following, but what was the reason we're not going over part 3 right now?
Because it's a little more mind-boggling than this is.
So we're doing that after.
Yeah, that I didn't say, so that's a very good question. We will be picking up with part 3 on Friday. It's just a little more mind-boggling. Definitely doable, but.
All right. Thank you.
Okay. Good question. So here's a picture of magnesium sulfate with its 7 waters of hydration. Cute, cute. This is actually the, let's see, yeah. The pink is the hydrated version and the blue is the anhydrous version. So do you see where you could take an anhydrous salt, like this cobalt 2 chloride, and it would be good at being a desiccant. And you'd know when your desiccant was spent because it changed colors. So let's see what sort of problem that might look like. I think I only worked 1 problem. The problem with these problems, what we run into in chemistry, is there's more than 1 way to work these problems. The phrase more than 1 way to skin a cat, I looked it up. It's not a meow cat, it's like a catfish. So different ways to skin a catfish, which is kind of gross too. I have skinned a catfish, but anyway, so we'll be dealing with nickel 2 chloride hexahydrate. And this is where I might, no, I don't think I'm going to do a picture of this one. The next one I am. So we're supposed to come up with what is the mass of, what is the mass percent of water? So if you have the hydrated salt, 6 waters of hydration for every 1 formula unit of nickel 2 chloride, what's the weight percent that's brought by your 6 waters of hydration? That's the first question we're going to answer. Then actually we're going to use that to our advantage and then knock out how much water do we have if we have 3.50 grams of the hydrated salt. So in order to work this, to have it make sense, I'm going to go ahead and knock out 3 molar masses here. So the molar mass of nickel, the anhydrous salt, nickel 2 chloride, we take 1 times 58.69 for nickel, plus 2 times 35.45 for chlorine. And we're allowed 2 decimals, so you got 129.59 grams per mole for the anhydrous salt. Molar mass of water, sometimes when you guys get started, you're like, I got that one memorized. So water, we'll take 2 times 1.008 for hydrogen, plus 1 times 16.00 for oxygen. So for water, the molar mass is 18.02 grams per mole. Then for the whole thing, how do we do it? Oh, yeah. For the whole thing, the molar mass, I just went ahead and picked up as 129.59 plus 6 of our waters, plus 6 times 18.02. So for the hydrated salt, for 1 mole of the hydrated salt, you're looking at a molar mass of 237.69 grams per mole. And we want weight percent of water. So remember what basically we're after. So weight percent H2O, that's going to be the mass of H2O divided by total mass. This would be of your NaCl2.6H2O. And to get it in parts per 100, so that's what we're looking at. And we're close here, aren't we? So, in chemistry, oftentimes working problems, it's good to have a basis. And the basis oftentimes is what you get to pick. Our basis is going to be 1 mole of the hydrate. So I usually, in my solutions, I'll say consider 1 mole of nickel 2 hexahydrate. Consider 1 mole, and let things kind of fall from there. Because if I have 1 mole, then I know, since its molar mass is 237.69 grams, I know I have 237.69 grams. And if that's the case, or if I have 1 mole, guess what? I have 6 times 18.01 grams. 6. Okay. So based upon that, I know because of the formula, I have 6 waters of hydration for every 1 repeating unit of that hexahydrate. Does this make sense? So it's as the basis we set. And notice that I'm, in order to communicate to myself as I work the problem and to communicate to the person reading your problem, which will be me, your work, you need to be explicit with regard to units. Okay, 4 sig figs. So you're looking at mass-wise, 45.49% of the mass is brought by water. Wow, almost half of it, water. So that means that if you take Like if you start out, if it was half. So if you start out with the hydrated salt, if you have 10 grams, if you zap it, heat it up, you're going to have 5 grams. Okay. So the second part of this question is we're going to use this to our advantage. I'm all about unpacking. So to unpack this percent, what that means is we have 45.49 grams of H2O in 100 grams of the compound, which is your NiCl2.6H2O. Okay, that's what that means, parts per 100. So with that in mind, the second part of the question was like this. Say if we have 3.50 grams of the hydrated salt, how many grams of water do we have? So this ratio right here, are we going to leave it like that or flip it? If I'm going to use that ratio to my advantage here. Flip it? I'm thinking leave it like it is because the grams of nickel 2 chloride hexahydrate need to cancel with the grams of the nickel 2 chloride hexahydrate, which is in the denominator. Does that make sense?
Oh, hydrated salt. I was thinking about just water.
Yeah. So, how many sick bags? Yep. I'm thinking 3 also. Since I've seen the answers to this one. 1.59 in units would be grams of H2O. So, I mean, it's just an exciting sort of problem. It means that if you were to start with 3.50 grams of the hydrate and dry it the heck out of it, you would lose 1.59 grams. Which makes sense. So speaking of drying the heck out of it, one more hydrated salt problem, and it's even more of a classic than probably this. Looks like this. And I'm going to kind of draw a little picture here. So we have copper 2 sulfate, but we don't know how many waters of hydration. Thus the little X here, .XH2O. So we're going to start out with a blob of CuSO4.XH2O. And we are going to heat it. And what's going to be driven off is the H2O. And we're going to end up with a smaller blob of the anhydrous. These are both solids, but so that's kind of what we got going on here. I like this because then I can put the numbers underneath. So this mass is 1.023 grams. The residue or the stuff that's left, this over here, is 0.654 grams. And here in a minute, do you see where we can get this mass by difference? Yeah. So this is 1.023 grams minus 0.654 grams. Cool. And so just to kind of take a bird's eye view of what we're going to do you see where in order to come up with this, basically what that is, X, how do I say this? We have X moles of H2O per 1 mole of the CuSO4, right? X moles of hydration per 1 mole of the anhydrous salt, kind of like we did on several slides ago. So this is what we're after. So do you see where once we have the mass of this, we can use the molar mass to get to moles of H2O. And we actually can use the molar mass of CuSO4 to get to moles of CuSO4. And once we have these moles, it's kind of like a little bit what you did in your calculations for the magnesium lab. We can simply take this moles, how do I say this? You can just simply take this moles divided by that moles to get the number of moles. I'll show you what I mean. Okay, so we're after the moles of H2O to the moles of the anhydrous salts to find X, basically. So let's knock out some molar masses. For the anhydrous salt, we'll take 1 times 63.55 plus 1 times 32.07 plus 4 times 16.00. So that's the molar mass of the copper 2 sulfate. We need the molar mass of water, and that's that 2 times 1.008 plus 1 times 16.00 for 18.02 grams per mole. And we're going to use that right here. So here we go. All sorts of oftentimes chemistry problems are just like little problems all put together. So here we go. Let's knock out the moles. But before we knock out the moles, we need to come up with the mass of the water. We said we can do that by difference. So if we take 1.023 and from that subtract 0.654, notice we don't do a lot of subtraction in chemistry, but since we are subtracting, we focus on decimals, not sig figs. So I got 3 decimals in both, so I'm allowed 3 decimals in my answer. So you're looking at a mass of water of 0.369 grams. All right, so let's knock out the moles of water. So we're going to use that. 0.369 grams over 1 is my first term. What's my second term? From previous slide.
It's going to be grams per mole of water.
Yeah, so what goes in the top?
Moles.
Moles, yep. 1 mole of H2O over 18.02 grams, exactly. Yep, molar mass of water. Usually that first term I put it over 1. My grams cancel, I'll be left with units of moles. Now notice here, it's like I said, well, I guess I didn't say this. The blue, the labels right here, I'm all about that, man. Because then you can go back and oh, I know what that was, okay? Now, if I didn't label it moles of water, then I think I'd have to be explicit. I'd have to put H2O next to the grams, H2O moles and grams. So titles can actually save you some time. So 3 sig figs, you're looking at 0.0205 moles of H2O. Okay, so here in a minute when we take the ratio, that's going to be in the top to find our X. So we said that we're going to take this 0.654 grams of the anhydrous. That's going to be your first term, 0.654, yeah, grams of CuSO4, or simply if I label it, I don't have to say what. Put that over 1. What's the next term?
1 mole over 159.6.
Yep, 1 mole over 159.62. Very good, grams. So grams cancel, we have units of moles. 3 sig figs, right? So you're looking at, oh, we get 2 leading zeros. That's exciting. So with 3 sig figs, you have, these don't count, they're placeholders. The 4 counts, the 1 counts, and that last 0 counts because it's a trailing 0 after the decimal. And we're almost done. Now this is where you hope that that ratio is going to be a whole number. Because if it's not, then we might have done something wrong. But if we simply go to see how many moles of H2O do we have for every 1 mole of CuSO4, it would look like this. Moles of H2O per moles of CuSO4. Divide that out, 3 sig figs, you get a nice round number, 5.00. And the units of that 5.00 would be moles of H2O per mole of CuSO4. And we've kind of come full circle. By definition, what a hydrated salt, this is, hydrated salts have a specific whole number of waters associated with every formula unit of the hydrated salt. So to answer this question, to finish that thought then, we would go ahead and say that this is a pentahydrate. We'll talk more about formulas and empirical formulas versus molecular formulas for part 3. But we would write the formula for this hydrated salt, CuSO4.5H2O, 5 waters of hydration. We pat ourselves on the back and say, yay! Any questions about that? So this part will also be due on Friday. That is Friday. Now tomorrow, Thursday's usually I need to check my mom dogs, but still, I will be here by 9:30 maybe. So if you have any last minute questions, just come on by. I go to lunch about 11 or so to highlight my day. So feel free to come on by if you have any last minute questions. Okay? All right.